here we want to prove the time shifting properties of DTFT. If we are given x of n is x of omega, remember in our table when we say that what happened to the DTFT of xn minus m, where m is a delayed version of, or xn minus m is a delayed version of xn. The answer was that we have x omega multiplied by e minus j omega m. Why is this so? Well, let's see. This is the discrete time Fourier transform equation. Here is xn minus m, so we put xn minus m here. We then substitute this as k, so x of k, and now all the index affecting n, to get back n over here, we have to be k plus m, because k equals to n minus m, then plus m becomes k again. Okay, so it will be xk e minus j omega k plus m. So again, we can now break this exponential up very quick easily, because we'll get e minus j omega k, so which is this term over here, e minus j omega k, and we also have the term e minus j omega m, which we will bring outside. Okay, so the proof of the time shifting property is nothing but manipulating the index and recognizing that E, for example, A plus B, J is equals to EJA, EJB. In the last slides, we'll just briefly discuss the existence of Fourier transform. When the sequence x of n is absolutely summable, okay? So imagine if you have this sequence here, 0, 1, 2, and all 0. Then of course this sequence has only values non-zero in these 3 points. So this is absolutely summable. So when the sequence has finite support, means a finite number of them is non-zero, the DTFT is guaranteed to exist. What about when the sequence grow, for example, and keep on growing and growing to infinity? Then it will not exist. So this is the basic check that we are going to need. In our course, we are not going to ask you to verify whether it exists or not. Now, the above condition is a sufficient condition but not necessary condition. What am I talking about? You realize that, hey, we are always playing with cosine omega n, a sinusoid, and the amplitude is 1. Therefore, its amplitude will always be spinning around. It doesn't die. So does that mean that the cosine does not have a DTFT? Well, you realize that in the past few examples, we have seen the cosine having a DTFT. And the key idea is that we are using the delta function. We admit the use of delta functions in the representation. Why this is true, we're not going to go into this. This is beyond the scope of this course. Okay? And of course, then even the step function has DTFT. And then you say, hey, but a step function, you cannot sum because it's going to go into infinite. So again, we are going to use a delta function within the step function. And the derivation is beyond the scope of this book course. Okay, with that, I think we're done. Thank you very much.